Hello, and welcome to Lecture 12 of AMAT502 at UAlbany. Today, we're going to be doing some of the math behind hypothesis testing and the Central Limit Theorem, two of the most important things for inferential thinking, which is one of the pillars of data science. Today's lecture is going to be slightly light on computation, at least using Python, as we're going to explore that more during our live exercises. So this lecture is really more of a math lecture. So the topics for today is I'm going to go over some of the basic hypothesis testing that you encounter in a first course in statistics, probably before you've even understood the basis behind where these hypothesis tests come from. That's going to motivate the second half of the lecture, where I'm going to try to go through a brief overview of some of the fundamental math that goes into the Central Limit Theorem, which is really what guides hypothesis testing. So, hypothesis testing is essentially what goes behind the statement whether or not an observation is statistically significant. If you have an observation, you want to know, is this worth changing my worldview? You're essentially asking a statistical question. And then behind that, I want to ask two further questions. So, when I'm determining whether or not something is statistically significant, I'm asking, does it call into question my basic beliefs? And the second question is, am I unwilling to attribute this to noise? Those are actually sort of two sides of the same coin. No pun intended. So let's consider an example that we brought up briefly in our live exercises from lecture 11. So suppose I hand you a coin and you flip it 100 times, and you get 62 heads and 38 tails. So based on that one experiment, would you believe that the coin is fair, or would you believe that it's biased towards heads? And then more to the point, how would you even compute the probability of observing such an event? We'll be able to answer both of these questions by the end of this lecture. So just to review, there are two fundamental approaches to probability. One is called the frequentist approach to probability. This basically says that probability is defined by counting the percent of time that an event occurs. So meaning if I flip a coin a bunch of times and I count up the number of times I get heads, then that frequency, the number of heads divided by the total number of flips, is the probability of my event getting a heads. Of course, if I only had access to this single experiment where I flipped my coin 100 times, got 62 heads, probably wouldn't be willing to go ahead and say that, the probability of getting a heads is 0.62, because that's 62 divided by 100. If I really adopted the frequentist perspective, I would feel much more comfortable if I repeated this 100 flip experiment, maybe another 50 times. Just to get a sense of what my frequency is amongst those 50 experiments. Now, frequentism is contrasted with what's called Bayesian probability. Now, again, math is still math, but if you want to understand the interpretation behind the math, this leads you to either the frequentist or the Bayesian perspective. So just for some history, the Bayesian perspective on probability is just as old as the frequentist perspective. But for whatever reason, Bayesian probability wasn't really broadly adopted because it required very lengthy and complicated computations. These computations were almost impossible to do without the aid of computers. And so now that we have computers, Bayesian probability has really come into favor amongst data scientists. So you should really get to know it. And so to understand the flavor of how Bayesian probability is different from frequentist probability, you should take this one sentence definition for Bayesian probability. Bayesian view of probability is that probability is how much you believe something to be true. Now, of course, when I have a coin, I can flip it a bunch of times. I can be agnostic about my beliefs and just do a bunch of experiments. That's what a good frequentist would do. But if I were asked a different question, let's say I was asked the question, what's the probability of life on Mars? I'd be very stuck if I were a frequentist, because in order to give an answer to this question, if I were a frequentist, I would want to somehow recreate the universe, let's say 1,000 times, and then in those 1,000 runs of my universe simulation, I would count, well, on how many of those universes did life on Mars arise? And then that frequency would tell me my belief or my probability of there being life on Mars. But obviously I can't do such a thing. I can't create broad scale simulations of the universe. And so in this particular question, frequentist approach to probability is useless. Instead, I need to adopt a Bayesian perspective. So let's see how that sort of rationale works in my coin flipping example. So the first thing we need to do is ask ourselves, what are our beliefs about coins? So I would say that it's reasonable to believe that if someone gives you a coin, then because it has two sides, and if I look and I check, this isn't a two-faced coin where I've got heads on both sides, then I need to really then it stands to reason that the chance of getting either one is equally likely, meaning 1/2 or 0.5. After all, the amount of engineering that you would need to take in order to manipulate my coin so that it would consistently bias towards heads or tails by some significant level. Again, significant I'm using it in an informal way, would require a lot of engineering. In particular, a coin is not really like jelly toast, where if I've got jelly on one side of my bread. And indeed, it turns out that if you try to flip jelly toast, 2/3 of the time, the jelly will land jelly side down. The toast will land jelly side down. All right, so let's use some of the language of hypothesis testing. So in absence of new evidence, what we believe to be true is called the null hypothesis, which we write as H sub 0. Remember, null is another way of writing, it's just saying 0. So that's why null hypothesis is our first hypothesis. Here are some examples of null hypotheses. So I already just said that it's reasonable to believe that the probability of getting a heads is 1/2. After all, two sides of a coin might as well both be equally likely. And absent advanced jelly engineering, it's unlikely that I'm biased particularly one way or another. Another example, which I just made up, but let's say that our scientific reports conclude that an aspirin helps headaches 60% of the time. So we want to compare our null hypothesis, which is our sort of original belief. Sometimes in the Bayesian perspective, this is called our prior belief. That's our prior, before getting any new evidence. So what do we do after getting more evidence? Well, we might need to update our priors. And in this case, this might lead us to reject our null hypothesis and consider an alternative hypothesis. So in statistics books, you'll see that alternative hypotheses are sometimes written as H sub A, where A indicates alternative, or H sub 1, which in Python is our second hypothesis. Okay, so what's a natural alternative in the two examples I just gave? So if I flip a coin and I got a bunch of heads, maybe I'm not willing to say it's biased towards heads, but let's just say I'm not sure this is a fair coin. I.e., what's probability of getting a heads is not equal to 1/2. So that's going to be my alternative hypothesis in that case. In my aspirin example, and this is one that ties in deeply to marketing and living in a modern capitalist world, is that all the time we're bombarded with new products. So let's say whatever company made aspirin is now trying to release a new aspirin, which they call aspirin extreme. And they claim that aspirin extreme is much more effective for treating headaches than aspirin. So you should always be a skeptic. And so your null hypothesis would be, I don't think aspirin extreme is any more extreme than ordinary aspirin. I think it's just as effective, meaning 0.6 the time, aspirin extreme is going to relieve my headache. So there we've formulated both a null and an alternative hypothesis. So let's see how we go about deciding between these hypotheses. So in our coin example, so if I have my coin example where I'm flipping it and I'm trying to decide, is this a fair coin or not? I'm going to take the simplest interpretation of what it means to be not fair, which is that probability is not equal to a half. This means that P could be above or below P0 or P naught, depending on whether or not you're British. So in this case, we use what's called a two-tailed test, and we follow the following decision procedure. First, we select the significance level alpha. So this is going to set how rare does our observation need to be in order for us to reject the null hypothesis in favor of the alternative hypothesis. The most common value for alpha is 0.05. This is why you'll often hear everyone says, I found something that satisfied a p-value of 0.05. We're going to explain exactly what that means right here. And the fact that 0.05 gets bandied about so much, that's exactly because it's such a common choice for alpha. Okay, so how do we get this p-value? Well, before we get the p-value, we have to compute what's called the z-score. Z-score measures the number of standard deviations from the mean that our observation lies. In this case, our observation x bar is viewed as this empirical mean or empirical average. That means we did our experiment, we flipped our coin 100 times, we got 62 heads, so x bar would be 0.62. We'll go through that example in the next slide. Okay, so we assume our null hypothesis is true, and then we say with respect to the null hypothesis, which comes with parameters. That's P0, it's the probability or percent of the time we expect to see something. And sigma 0, which is the standard deviation of the null model. So with regards to that, by using the fact that we're doing this n times, we're doing some sort of experiment or observation that's averaged over n individual observations, we compute z to equal x bar minus p0 divided by sigma 0, which is over square root of n. Of course, if you had to simplify that fraction, the square root of n would go up top. Okay, so that's the z-score. Now, the z-score just tells you where away from the mean are we, assuming we have a normal distribution. And so what we do is then compute the probability of getting an observation at least as extreme as the one we observed. Now, in the two-tailed tests where we say it could either be above or below the mean, we don't know which, the way we compute our p-value is we take the area under the curve to the left of minus absolute value of z, it's over here, and we take the area under the curve to the right of absolute value of z, that's over here. So that gives us twice, because of evenness, that also is equal to twice the area of just what's underneath here. Notice that this number here is exactly the same as this number here. That's because Gaussian or normal distribution is an even function. It means it's symmetric about the y-axis. And then our final rule is that if our p-value, which is whatever this probability is, the area under the curve and those two tails, because we're using a two-tailed test, is less than alpha, then we reject the null hypothesis in favor of the alternative hypothesis. And so you'll see here in this table here, they've actually gone ahead and computed the critical level for the z value, which will cause us to reject the null hypothesis. So if we use a significance of 0.05, that means we need to be more than 1.96 standard deviations away from the mean. Again, that makes sense because of the 68, 95, 99.7 rule. I told you that roughly 95% of all observations are within 2 standard deviations of the mean. So that means we need to be further than 2 standard deviations from the mean to be in that 5% of all observations. So our coin example then operates as follows. Our null model is that the coin is fair. That's 1/2 is the probability. I'll tell you how we compute sigma 0, but right now I'm just going to tell you it's the square root of 1/4, which is 1/2 times 1/2, which in turn is equal to 1/2 when I take the square root. Our alternative hypothesis is that p is not equal to p0. We don't specify whether it's above or below. So this causes us to use a two-tailed test. When we flip this coin 100 times, that set our value for n. And in particular, we got our empirical average by taking the number of successes, the number of heads divided by n. 62 divided by 100, which is 0.62. It's also sometimes called our sample mean. We take a sample and we compute our mean statistic from that. So our z-score is then 0.62, that's this value right here, minus p0, that's 0.5, where I then divide by sigma 0, which is 0.5, which has been scaled by the square root of n, square root of 100, which is 10. So then when I multiply this all out, I end up getting 2.4. So if I look up, and this is how we did do it back in the day before we had Python. So if I looked up my z table, I want to know what's the associated p-value. Well, the area to the left of minus 2.4, that's our z value, is 0.0082. Now due to symmetry, I can just take 2 times 0.0082 to get 0.0164. Now since 0.0164 is our p-value, and that's less than 0.05, we reject the null hypothesis in favor of the alternative, i.e. this coin is not fair. So let's consider another example, or another test. This is called the upper tail test. Here we modify our alternative hypothesis to say that p is greater than p0, i.e., or I should say e.g., heads is more likely than 0.5. The only thing we need to do now is that in step 3, when we compute our p-value, we change it to just compute the area under the curve in the upper tail. That means to the right of my z-score. You'll notice that because I don't need to sort of divvy up the area across these two, my critical z-score actually goes down to 1.645. So we just computed back here that our z-score was 2.4. 2.4 is higher than 1.64, which means there's less area to the right of 2.4, which means that my p-value is 0.008, which is going to be less than my 0.05. And so consequently, I reject the null hypothesis in favor of the alternative hypothesis, which in this case is that it's biased towards heads. And I actually need less evidence, so less of a split towards the number of heads in order to reject the null hypothesis in favor of this hypothesis. So that was a little too easy. Let's go ahead and change our significance level alpha. And maybe let's ask for an order of magnitude difference. So I'm gonna go from 0.05 to 0.005. In our coin example, we got, again, z to equal 2.4. But that's less than the critical or the threshold z value given there, which is 2.576. So for this level of significance, 62 heads would not be sufficient. And so we would not reject the null hypothesis. But we're actually very close. So let's just go ahead and calculate how many heads would I need in order to reject the null hypothesis in favor of this alternative hypothesis at the significance level, which is 0.0005. I may have said too many zeros. Yeah, 2 zeros, 5. It's 0.5%. Well, I could set my z-score to be equal to my threshold, which is 2.576, and then do some math to solve for x bar, which would be 0.5 plus 0.05 times that, which is 0.6288. So in fact, if I'd gotten just one more heads out of my 100 flips, then I would have had enough heads to reject the null hypothesis in favor of the alternative at this stricter level of significance. That's a repeat. So the lower tail test is exactly as you might imagine. Now, in order to compute my p-value, I just look at area to the left of my z-score. So again, you need only minus 1.645 standard deviations below the mean in order to reject the null hypothesis in favor of another hypothesis which asserts that p is less than p0. All right, so hopefully a lot of that was familiar to you from either a high school statistics course or a first-year statistics course. So the real question goes to, why was I able to take something that involved coin flips, where, obviously there are only discretely many possible outcomes, and instead use area under the curve and use a normal distribution? So how do I go from this coin flipping to the normal distribution? To understand why, we need to review some discrete probability. And this goes to the math behind hypothesis testing. So some of the language that you might hear as you advance through your studies is that when we study probability and probability distributions, we simplify their study by looking at what's called summary statistics, i.e., these are things which summarize our distribution. The two most common summary statistics are the mean and the standard deviation. So the mean is also called the expectation. And the way you compute that, and that's written sometimes mu sub x, it's the Greek letter mu. It's also sometimes written as e of x. It's our expected value for x, where x is a random variable. Is I sum up all the possible values for x. That's given by these little x's, and I multiply by the probability of that value. So this probability here of that value is what's called the probability mass function. It's the PMF. The variance, on the other hand, is what's called a higher moment, or it uses a higher moment of the expectation. This asks how much does the random variable x vary from the mean. And I want to not have this sort of feature where varying above and below cancels out. So I square this to make sure that every time I vary, I'm adding up some positive number. So it turns out with a little bit of work, you can show that this is the same thing as e of x squared minus mu x squared. Or again, mu of x is computed using this formula. So that's the variance. And so the way you compute the expectation of x squared is you take exactly the formula that you used for e of x, but you square all the values. So this essentially has the effect of sort of making anything that was negative positive, but it also sort of pushes out values farther and farther. And the standard deviation is, of course, the square root of the variance. So that's why we just write sigma x, whereas the variance is sigma squared. All right, so what are some classical discrete random variables, and what are their means and variances and corresponding standard deviation? It's the fundamental building block. It's the Bernoulli random variable. This is a variable that takes the value 1, the probability p, and takes the value 0 with probability q, where q is equal to 1 minus p. So that means that probability of either 0 or 1 is 1, because you add up p and q to get 1. We can express the PMF using this table. Now, the interpretation of a Bernoulli random variable, again, the hardest part of math, especially when you're doing applications, is knowing how to interpret your math in terms of your model. So we interpret whenever our random variable x equals 1 as a success. And we do this when we're performing a trial where there's only 2 possible outcomes. For example, head or tails, pass or fail. All these are examples where we only have 2 possible outcomes. We can model them using the numbers 0 and 1. So x equals 0, x equals 1 would correspond to getting a heads, for example, and x equals 0 would correspond to getting a tails. So what's the mean and standard deviation for a Bernoulli random variable? Well, if you follow the formula, I just take my value, 0, times the probability of 0, doesn't matter, because anything times 0 is 0, plus my value 1 times probability of 1, which is p. which gives me P. This goes to the whole fact that, if I'm flipping a coin where the bias is P, then I expect to see the number of heads P% of the time. You run through the variance formula. I go through that same calculation except where I square 0 and 1. I've dropped little dots in between just for space. So that gives me, 0 plus P, and then I subtract my expectation squared. So P minus P squared, which I can factor into P times 1 minus P, which is P times Q. So in our coin example, remember we just did this when we computed the z-score. So we can use the fact that sigma 0 was equal to the square root of the variance. The variance is P times Q. But again, here we thought of P as being the probability for our null models. We just use notation P0 times Q0. The Q0 is the same thing as 1 minus P0. So in effect, what we're doing was using the standard deviation of a Bernoulli random variable associated to the null model. The next most fundamental part of discrete probability is what's called the binomial random variable. So you can think of the binomial random variable as the sum of n Bernoullis. So if I model my coin tosses where 1 is a heads and 0 is a tails, then the random variable that counts the number of heads is equal to the sum of my n Bernoullis, i.e. Sn, which is equal to x1 plus on through xn, has a binomial distribution. Again, IID, just as a reminder, means independent and identically distributed, i.e. each of these xi's have the same mean, P, and the same standard deviation, square root of P times Q. So instead of writing out that table, because here it's a little more complicated, if I want to know the probability that I get k successes out of n tries, I need to choose the k times where that occurs. So that's using this choose formula, n choose k, times the probability of that particular sequence of events. So k successes and then n minus k failures. So obviously when I'm flipping my coin n times, this is an example of where I have a binomial distribution counting the number of heads. So let's figure out what's the mean and standard deviation for these random variables. So two other key concepts, which I'm hoping is just review for you. So linearity of expectations is that whenever I have a sum of random variables, I can always compute the expectation of the sum in terms of the sum of the expectations, i.e. the expectation of Sn, which is by definition the expectation of x1 plus on through xn, is equal to e of x1 plus dot 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 plus e of xn. Now since each of these was p, I have n p's here. That's n times p. Now, variance is not linear, but it is for independent variables. So since I assumed not only were these guys identically distributed, which allowed me to conclude this, I assume they're independent. So that means that the variance of the sum is the sum of the variances, which we just computed was p times q. So I have n p times q. So in particular, the standard deviation is the square root of n times pq. All right, so practical example. If I flipped a fair coin 100 times, then obviously I would expect the average number of heads to be 50. That's 1/2 of 100. But the standard deviation would be square root of 100 times 1/2 times 1/2, which is square root of 25, which is 5. So that means a single standard deviation from the mean is about 5 heads, either above or below. And so in particular, 95% of all observations would occur with either 10 heads or 10 tails, or 10 heads above or below the expected value. So this means a very quick rule is if I want to decide whether or not my coin was fair, I use my two-sided test, flip it 100 times, and if in that try I got either more than 10 above or 10 below, I would reject the null hypothesis. All right, let's put all this together. Let me remind you of one of the most fundamental forms of the central limit theorem. So the central limit theorem in general is a convergence theorem, which says that if I sum up a bunch of IID random variables, and these could be discrete or continuous, they could be of any type, they don't need to be Bernoulli, then it converges to something which looks like a normal distribution after I've done some appropriate scaling. We'll define what that appropriate scaling is shortly. But for our purposes, you can think of the following as a good rule of thumb and approximation for doing data science when you are looking at Bernoulli trials, i.e. coin flips, or for example, coin flips. So Sn, which is going to be the sum of n Bernoullis, which is distributed as using the binomial formula I just gave you. So if I have a binomially distributed random variable, and this variance is greater than 10, so that's n times p times q, then the following is a very useful trick for computing my significance or computing the probability of my binomials. In particular, if I want to know so if I want to compute the probability of a binomial random variable being between two values, and I can think of these as real values, a less than b, then I can use the area under the curve associated to the normal distribution, which is implicitly what I was doing when I was computing the z-score. So just as a reminder, we sometimes use this capital phi of s, which is the integral from minus to infinity to s of e to the minus x squared divided by 2 divided by the square root of 2 pi. This is the CDF, cumulative distribution function, associated to a unit normal distribution. So what the normal approximation of the binomial theorem says is that under the assumption that np times 1 minus p is greater than 10, then I can approximate the probability that my binomial random variables between these two values, a less than or equal to b, by instead working with what's called the z transforms of a and b, where I subtract the mean of Sn, that's np, and I divide by the standard deviation, and I can convert this, use these values to plug in to compute the difference between the CDFs of a unit normal valued at b star, that's this standardized value for b, and a star. And these again are called the z transforms of a and b. So just to make it a little more concrete, if I want to flip my coin 100 times, and I can ask, can I use this approximation? Well, yes, I can, because n is 100, p and 1 minus p are both a half. So this gives me 25. 25 is greater than 10. And in fact, as long as I flip more than 40 times, I can use the normal approximation to a binomial. And then this allows me to compute the area under this probability in terms of the area under the curve of a unit normal distribution. So since we use that calculation where we subtract the mean and divide by the standard deviation so much, it's really important to go ahead and give that a separate name. Sometimes this concept is referred to something else, but we can call this the z transform, where we basically standardize our units. We take our random variable x, we subtract its mean, we divide by the standard deviation. This gives us a new random variable z. And essentially this just measures how far from the mean we deviate. And again, using those properties of expectation and variance I alluded to earlier, we know that the mean of z is 0 and the standard deviation is 1. So in essence, what the central limit theorem says is that if I take the z transform of a binomial random variable, this looks like, or tends to, a unit normal. So now we can put everything together. So remember, when I was talking about hypothesis testing, I used x bar. X bar was our sample mean, or empirical mean. Really, that is itself a random variable, right? I take a couple flips and then I divide by the total number of flips. That gives me some random number. And in particular, I can think of that as Sn, which is the sum of my heads, divided by n. So if I want to go through and see how does the normal approximation allow me justify my use of z-scores, all I need to do is follow the following few calculations. So remember, our null hypothesis was that our coin was governed by some probability p0, which we took to be a half. From this, we computed the null model's standard deviation, sigma 0, which is the square root of p0 times 1 minus p0, which was a half. Square root of 1/4 is a half. So if we look at the expression we just used in the normal approximation to the binomial, we had this. It looked very, very close, but on its face, it's still different because here I have Sn and here I have n times p0. And whereas in the way we calculate our z-score, sigma 0, we divided by the square root of n. Here we have it multiplied by. But we're one step away from getting exactly the expression that I used in that hypothesis testing procedure. So if I factor out n, then I can do that by introducing a 1/n for Sn. So I pull n out of this expression and I get n times Sn divided by n. Obviously those cancel. Minus p0. Because if I multiply through, then I get my n times p0. But we know what this is. This Sn over n is our x bar. But let's pay attention to what happens in the denominator. So I'm dividing by, here is sigma 0 square root of n. Now, obviously, if I have an n and I have a square root of n, this is n to the 1/2 and this is n to the 1. So I can cancel some of the exponents to get the square root of n up top. But that's the same thing as in our denominator, dividing by the square root of n. And plugging in Sn over n equals x bar gives us exactly the expression we use for computing our z-score. So moral of the story is, if I really want to apply hypothesis testing, first of all, I need to be sure I'm in a setting where I can use this normal approximation to the binomial, or I can use the Central Limit Theorem. In this case, n times p times 1 minus p needs to be greater than p, or 10. So for us, flipping a coin, fair coin, we only have to flip it 40 times. Then that allows us to, instead of computing with the probabilities directly of binomial random variable, which is pretty complicated because it involves a sum with a bunch of choose coefficients, we instead just use the unit normal, for which there are standard tables that we can look up, like in here. Now, all this felt like a little much. I encourage you to read some of these other articles. This one basically goes through exactly what I described today. But really, this being a master's level course, I'm assuming everyone's had a first course in probability and are ideally taking higher level probability and statistics courses. Some of my favorite books include Grinstead and Snell. This has the advantage that it's basically available online for free. I think got it pulled up over here somewhere. Let's go ahead and click on the link again. So this was turned into a PDF. It's freely available. And this goes through all the basic probability that you would need for a statistics course. Now, I also like this book. It's not free, it's harder to find. And it is essentially given another approach to doing the same material as Grinstead and Snell. From there might, some books you might like to go for more higher level statistics. This is Hogg, McKean, and Craig. Or DeGroot and Shervish. These are standard statistics textbooks. Now, there are, of course, computational versions of all of this, and we're going to get into that during our live exercises. But I wanted to refer to you one of the institutions that's really, I think, leading the way in terms of data science education. That's UC Berkeley. And they have a course where they've designed a textbook which goes through essentially all of either Grinstead and Snell or this other book by Anderson, Sipilainen, and Valko, and have used Python alongside of it. This is actually a follow-up course to another basic data science course called The Foundations of Data Science, which has an associated textbook called Computational and Inferential Thinking, which is an inspiration for some of what we've been doing here today. So I hope some of this was a useful and insightful reminder of how hypothesis testing works and what is some of the mathematics that goes behind it, and done in a little more detail, what you might expect at a graduate level. I look forward to seeing you all in class.